Okay, let's see. Are we streaming? Looks like we're streaming. I think we can get started. So, all right. So, we get started. This is important. That's also okay. All right. So, today's topic, or rather, today is actually I was working on something and thought it would be a good topic to sort of just do a very short talk about. And so what we'll be talking about today is basically parsing device trees for mmio addresses. This is a very simple way of saying that we have so Linux specifically uses a particular kind of a particular method for hardware discovery. So for example, if we have the Raspberry Pi, or we have some other kind of board like the BeagleBone Black, or more professional SoC, or an evaluation kit like something like the NXP IMX8, or you name it, pretty much any board that you have, the peripherals that are present on that board, along with the description of those peripherals and the different kinds of peripherals that are present on the board, is something that usually in the past, if you were working with Linux, you would see that they were sort of hard coded into the source code itself. But then came this thing called the device tree. So the device tree is basically it's a tree. It's a tree of what you call nodes. Let me actually show you what that looks like. So I hope this is visible. Let me just quickly check the chat. Yeah. Let me just see. Is the font's visible? Is the font size okay? Or is the font size okay? Okay. So, well, yeah, I guess so. Okay. So let's actually switch to the DTS page. So if we were to look at a device tree, if we were to look at the source of a device tree, so a device tree is usually something that's written in the textual format that you see over here. You have it's actually a hierarchy of nodes that you describe in the DTS file. The hierarchy is something like this. You got, starts with the root. Actually, it starts with the version number. But anyway, then you have the root. Then you have aliases. And then, all of these ones in, say, blue are actually the nodes. And then each node has properties. So for example, if I wanted to describe, or if I wanted to give, provide information about a particular peripheral that's present on the board. For example, this particular board that I'm using is for the IMX8 M Nano, because this is a board that I've been working on for some time now, just adding a couple of things. But if I wanted to show you something like, let's say, I don't know, let me just say UART. So these are not the actual UART peripherals, but if I went, okay, let me try something, I know, a little simpler. So that's I2C, should be good, right? Okay, yeah. So here you see that the I2C node, the node actually talks about, or rather describes, the peripheral in such a way that it says, okay, this particular peripheral is mapped into memory at this memory address, which is 30820000. That's the base address for this peripheral. In other words, when we talk about memory mapped IO, we are primarily talking about, any way to interface with a peripheral is done via memory. That means you basically read and write to some location in memory, and that location is being specified directly over here. And also the size of that, that memory address range. So basically, this is nothing but, a memory address range that represents the peripheral's registers themselves. So that's why the field is called reg. So the idea is, I was just looking at this and saying, whenever you want to build, whenever I want to build a driver for, let's say, one of these peripherals that's on the board, I usually have to dive into the data sheet and find out, all of these details, like what's the base address, what is the size of this particular address range, what sort of interrupt numbers are we looking at, what are the usual pin names, and what are the pin numbers that we should be using, which could be, some of these peripherals could use default pins, etc. So all of that stuff is usually something that is information that we require if we were to configure this device properly, or configure this peripheral and use it properly. And that information is present in the device tree. Okay, so yeah, let me just quickly check the chat. Okay, yeah, so Anand says font size is okay, good. So that's predominantly what we talk about, what we refer to when we say device tree. Okay, now the point I was looking at was, I said you could, for example, if I wanted to, let me see if I still have my data sheet here, or I sort of misplaced it because I keep doing that. So where did that go? Okay, so it's not here. All right, so basically, let me just Google it. Let me try and find it. IMX8 MN reference manual. Right there. Okay, so this is what you'd have to read. This is about 3,000 pages, and it's obviously it's well documented and stuff, but you'd sort of have to dig through this and figure out exactly all of these details. And sometimes you might not find this documentation, at least it's not readily available, or rather easily available to you. So for example, in this case, if I wanted to actually go and check what the same information that I wanted, rather than, if I didn't have the device tree and I was looking at the manual, I'd have to sort of jump into all of this, and I'd have to go to, let's say, yeah, you have to go through all of this, and then I'm just looking for very simple things. I'm just looking for the base address. Where does this, where is this peripheral mapped into memory, and sort of what's the memory address range? And then I find it, right? So you see the same thing over here. So the absolute address is this, and then you see all the registers that are mapped, and they are offset values as such. Sorry, these are the reset values, but you also get the offsets for each of them, because if you look at it, this is a 16-bit register, so you get the offsets. So that's pretty much how you would normally try to, you'd normally refer to data sheets and you'd pull them out of there. But as I said, this was a big problem with, prior to the device tree coming into use. And now that we have the device tree, this is like the single source of truth. Pretty much every vendor provides, when they actually provide their images, they also put together a device tree in source that can be compiled into a binary blob. And that binary blob is what Linux uses to discover all of the different peripherals on the machine. Of course, this is not the same method that, let's say, some other architecture like x86 64 uses. They use things like there you use things like ACPI tables, etc., which is a little different. But nonetheless, in this case, in the ARM world that I'm specifically referring to, you would normally use a device tree. So the idea was, I was just thinking, because I'm working with that board, I thought, and I'm going to anyway be doing a lot of this, adding a lot of support for a lot of these boards. Why not just figure out a way to sort of make this a little more simpler so that you don't go running around to multiple different places for this kind of info. So that's where, started looking into device trees. And then now let's look at device trees. So I've already shown you what a device tree looks like. It looks like, where did that go? Yeah, sorry. It looks like this, right? It's a simple, it's a simple textual file. It's a simple text file. It's got, it basically lists a bunch of nodes. Nodes in this case can be peripherals, can be other things, and those nodes can have properties. And they are usually nested nodes, nodes within nodes within nodes. The idea is we need to sort of figure out which node we want and sort of pull it out of there and then parse it and say, okay, then we get the information that we're looking for, exactly what we're looking for, right? So yeah, I hope that sort of makes sense, right? It's pretty trivial. It's, I wouldn't say trivial, but it's pretty straightforward. So the first thing that we normally need to do, let me look at the goals that I have for today, which is, so how do you actually parse, or rather, before we get to parsing the DTB, we'd want to understand what is the device tree format like. So there's actually two things. One is the device tree source, which you just saw, which is this. And then you also have the flattened version of it, which is nothing but saying that you convert the DeviceTreeBlob into a binary format. And that's your, what we call the DeviceTreeBlob or the flattened device tree. It's also called FTT, etc. Right, so we'll take a look at the flattened device tree format. So what I have over here is, this is the specification, the actual spec for device trees. So if you look at it, it says, the device tree for blob is, I hope you can see this. Yeah, that should be good enough. So the device tree blob format is a flat binary encoding for device tree data. It's basically used to exchange data between software programs. Oh, by the way, this is not just limited to Linux alone. It's being used pretty much everywhere. I mean, any kind of software that has some scale, I see that it tends to use device tree format in some form or the other, because it's more or less sort of a standard right now. Oh, a pretty popular standard, let's put it that way. But coming back to the flattened device tree, the flattened device tree is basically, it's just it's just a bunch of bytes. As they say it, it's a single linear pointerless data structure. There are no pointers here. You have offsets, but there are no pointers in the data structure. Basically, the way it works is there's a header in the blob. I'll be showing you some of that. There's a header, and that header is 40 bytes. That's the standard. There's 40 bytes, and then you might have some padding after that. Then you might have what's called a memory reservation block. A memory reservation block is basically, a space, a small amount of space that's allocated for reserved memory in the device tree. So for example, if they've sort of mentioned that over here, the memory reservation block provides the client program with a list of areas in physical memory which are reserved. That is, which shall not be used for general memory allocations. So for critical pieces of your system, when you're trying to protect data structures that are vital, as they say, from being overwritten, they're saying, okay, let's just call that our reserved memory block, which we don't want anybody tampering with. So we'll just call that that. That is also something that you can mention in your device tree. So when you say that, it basically means that you're saying that these portions of RAM or whatever, they are sort of reserved. You don't want to actually mess with them because that's critical for system functioning. And then come the interesting parts, which is the structure block and the strings block. The structure block is actually what contains those nodes I was showing you, these nodes. The structure block actually contains that. And then the strings block is just a set of strings. All null terminated strings are present in the strings block. All right. I hope so far it makes sense. Yeah. Okay. Questions? Yeah, I'm sort of running through this because I thought I'd keep this short and not too long because it's a very small topic anyway. Okay, I guess not. So let's just go. So that's pretty much the breakdown of what a DeviceTreeBlob looks like. And now let's actually sort of look at, what does the DeviceTreeBlob contain. So what I'm going to do right now is, I actually had this on my thing. Yeah. So one of the things that you can do is there's also something called, so you might be wondering, how do I go from this, which is a source blob? This is a source. How do I go from this to the DeviceTreeBlob, the flattened DeviceTreeBlob I was saying? So you can do it two ways. One is you can do something like this. There's a DeviceTree compiler. It's called DTC. So I hope this is visible as well. It's called DTC. So you can take the DeviceTree compiler can compile from source to DeviceTreeBlobs, and you can also go the other way. You can give it a DeviceTreeBlob and it'll spit out the actual source. In fact, that's what I've done. I didn't have the source for this particular file. I actually pulled it out. So if I did something like this, yeah, this is my DeviceTreeBlob, as you can see. So you can see that that's the DeviceTreeBlob for my particular board, and I'm providing it an input, which is DTB, and the output I want is DTS, is what I'm saying, and I provided the DeviceTreeBlob. If I just go ahead and hit, enter. Okay. Oh, sorry. I think I misplaced it. Let me try that again. Wait, I think it's examples. Yeah. See, the same file that's on the left, which is this same file that's on the left is here. So I'll just scroll to the top so that you can see it clearly. Yeah, this is not a very big file, but it's pretty lengthy. It's about 30 kilobytes usually. Usually DeviceTreeBlobs can range from somewhere to 20 to about 100 and 150 as well, depending on how big of a, how much you want to actually convey using that DeviceTreeBlob. Okay, so it's the same thing exactly. So I can go ahead and either decompile it or compile it using the DeviceTree compiler, right? That makes sense. Then I wanted to show you that now I can also do something else, which is I actually want to go ahead and sort of examine the actual bytes, because I told you that we've got a DeviceTree header, then we've got the reserved block, and then we also have what is called the structs block, and then we have the strings block. What does that mean? I mean, what does that look like in the binary format? So the way to examine that is, we can just use something like hex dump. So I'll start with start at the top. I'll say, because I said there's about 40 bytes of a header, right? So let's look at that. So I'm going to do examples, and then I'm going to say whatever that is. Yeah. So if I just go, so you see that this is what you get. All right. And this is the let's just look at the, I'm not going to go through all of this, but just to give you a sort of an understanding of what we're dealing with over here, because this is very, It's very straightforward, actually, not much over here. But since it's useful to sort of learn about, these different formats, because they can get a little involved when you actually start implementing the parser, etc. So let me actually pull up the, the spec again. So yeah, here's the spec. So as I said, the header contains a magic value. As you can see, the magic value is D00D-FEED, which is basically some hexadecimal characters that we consider as the magic field for your flattened device tree header. And that's exactly what we see here, right? And now you can just start counting the next 4 bytes. So by the way, the device tree header likes 32 bits. Pretty much everything in the device tree header is 32 bits. It's 4 bytes. If you want to pad something, it's usually, you can do it within those 4 bytes. If you want to align something, it's 4 bytes. Yeah, so this is pretty much, it's pretty much 4 bytes is what you use for everything over here. It sort of makes it easy. So, and you can also see that the total size of the, of the device tree is actually hex 89A0. So if I did hex 89A0, I get 35232. So if I was to just look it up again, in here, I get the same value. So okay. So basically you can sort of pass through the header and figure out, you're dealing with the right header, you're dealing with the right pieces. And as I said, it's a pointerless data structure. So everything about this data structure is, or this binary blob, if you want to find where the struct portion starts, there's an offset that's baked into the header. If you want to find out where the strings start, there's an offset that's baked into the header. Likewise, there's a whole bunch of different things anyway. So in our case, what we wanted to do was we want to take this and basically we want to pull out, let's say, if I give it an I2C, if I say, look, I want you to provide me the, all of the different mmio addresses for the I2C peripheral on this particular device. Now, just to be clear, there's not one, but there's at least 4 I2C peripherals for this device, right? There's at least 4 of them on this device. So we'll have to see how we can parse this to get those 4. That's the simplest thing that we're doing today, because as I said, we like to keep it short. Even just discussing this has taken up more than 20 minutes. Okay. Let me check the chat. Any questions? What language do we use to make the script? It's simple. It's straightforward, basic text. There's no specific language as such. It looks sort of like, it's basically a bunch of key value pairs where if you look at this, it's straightforward. It's like you just start off by saying, okay, here's my version number, here's my root node. Then you start with your flower brackets and just keep going through, or your curly brackets, and you just start adding properties to it. The important thing is all of these property names and node names, some of these are actually standardized, and that's part of the spec. So that's something that you need to keep in mind when you're writing the device tree. And this is usually not written manually. It's all, extensions on top of extensions. So you already have one format, then you keep adding to it. People just keep doing that. And there's a bit of tooling that is used to sort of automate all of this. But yes, it's written in just plain text. And there are obviously tools that understand DeviceTree's source files pretty nicely. So you can get this nice syntax highlighting piece, etc. for it. Right? I hope that makes sense. I hope that answers the question. Okay. All right, good. So yeah, now let's quickly, enough talking about this, let's just jump directly into some of this parsing stuff and let's see how we parse stuff. So I've actually been messing with this just a couple of hours before this session. And I think I've done a couple of things, but I thought I'll just write them down anyway. So the way we're going to do this is we're simply going to say why do this way? Since I've already written it, let me sort of walk you through one by one. So if I just uncomment some of this, just so that you get it. So we simply go ahead and create a buffer, a vec, and then we we open it up. By the way, we're doing all of this in a standard environment. We're not doing this in a no standard environment, so we're free to use the heap as we like, right? That's another part. So you need a buffer to pull your DeviceTreeBlob into it. That's what we do first, and then we go ahead and and then we go ahead, as I said, we go ahead and read the file in. This is what we're doing over here. We're reading in the blob, and actually let me just expand this a bit. We read the blob in, and then there is a particular type called reader that I'm pulling in. This is something that I've already written. So the entire parsing logic is already implemented as part of my library. So I'm not actually walking through that piece because that might take a little while and it's not that interesting anyway. It's straightforward. It's just parsing stuff, right? Let's look at how you can actually parse this and sort of gain that information. Of course, I'm yet to make it pretty and actually make it really usable or turn it into a tool or something that is very quickly usable. I've not done that yet. I'll probably get that done by today and see if I can roll that out. But anyway, so I'm pulling in what's called a reader, which will allow me to read the buffer. So this entire lines 19 to 27 is basically set up. I'm trying to allocate some memory on the heap, which is in the form of a vector, and I go ahead and sort of read my DeviceTreeBlob, which is being provided as an argument to this program. It'll be pulled in, and then I have this reader type that's actually going to read and parse everything so that I can start using it. Then let me actually go to the next part. The reason I'm walking through this way is because it's faster. Just don't need to worry too much about some little string manipulation problem, because string manipulation can take away a lot of your time. So I thought I'd just do it this way. So log init is don't worry too much about that. That's just because we have a library that we've written, so I'll show you that library as well, just so that you know. So in rustboot, we have the source, we have a device tree parsing logic fully that's built out. We can also do things like patching the device tree, etc. That's also some support for it that's already built into the device tree parser. So this is the library. This is the, these are the set of modules of the library that we're using to parse our device tree. So in simple terms, if I was to go and let's take it step by step. If you were to see, if you see this over here, I'm trying to actually read the I2C, I'm trying to actually parse the I2C peripheral and then figure out what the base address is and etc. All the different properties in that particular node. So luckily, there's also an alias node over here that gives me the entire set of I2C buses that are, or I2C peripheral that are present on this board. So the actual path, as I said, the device tree is actually a hierarchical set of nodes laid out in this manner, right? So you start out at root. So this is the root, which is the first slash, and then sock at 0 is the first node. Then there's a node underneath, there's a node within it called bus. There's another node within it called I2C, which is at this particular address. That's how you would normally traverse the device tree. That's why it's called the tree, and figure out which which particular I2C am I talking about. This is how you do it. So what I've done is here I've basically said, reader, which is my device tree reader. I want you to look inside the struct items, and then at this particular path, I'd like you to pull the node out. Give me the node. And that's what you see over here, which is what I get, which is my node. It returns one of the items in the structure, the struct block, returns one of the items. I take that item and then, I'm just going to do this. Let's just go ahead and print this and see what we get first, right? All right. Where was my example? Okay. So right. So if I were to run this, I think this is correct, huh? Yeah. So if I was to run this, I'd like to turn off all of my error messages. So just to keep it simple. All right, so I get one value that's printed to the screen. Let's look at that. Let's look at what that is. Let me just minimize this here. So what's happening here is I am looking at, let's actually, I was going to actually show you that particular field, right? So if I wanted to show you that field, so here's the root, right? This is root. Now I need to find SOC at 0 first. So let me go find SOC at 0. Yeah, this is SOC at 0, right? Now within SOC at 0, what's the bus number? Which bus am I using? I'm using bus 308, whatever that is. Okay, that's where my I2C bus is. So if I go back and look at it, so not this bus, I should be looking for another bus. Okay. Yeah. Okay, not this bus. This is 304. Yeah, this is the bus that I'm interested in, which actually, connects my I2C peripheral. So within this node, I will find my I2C bus. All right. So that's the path traversal that I need to do to effectively find my I2C node. And when I find my I2C node, all I'm trying to look for after this is I'm just trying to look for these three, actually the registers, the interrupts, and then the pin control names, or rather the pin control, if there's any specific pins that we're supposed to be using for this peripheral. That's the kind of information that I want, and I want it quickly. Not that we can't find it from a data sheet, we can. It's just that, rather than run through that, we have something that's like the real source of truth that, let's say, Linux uses, or other operating systems like OpenWRT, etc. All of them use this, or use a device tree. So this is pretty much a source of truth. We can consult the DeviceTreeBlob, parse it, get what we want, and not worry too much about running around here and there for this information. Right. Let me just take a pause. Any questions on this? Okay. Yeah, so I'll just quickly go through because I think we're almost done with this. Okay, so that's, if I wanted to look for this particular node, now I know that this node has this path structure. I just go ahead, traverse the path, get my, I'm printing the offset out over here. That's what this value is, by the way, 20040. What I'm trying to say is, if I was to sort of verify this, am I actually doing what I'm doing, or are you just taking my word for it? So yeah, so if I just say 20, that's 20,040. If I was to go ahead and print, oh wait, no, I want to print just 8 bytes, let's say, from there. But I want to print at this address, which is x20 40, right? I want to print this offset into the device tree, right? That's kind of okay. That's also not the offset, sorry. X 20 40. Yeah, I think that's, sorry, my bad. I keep getting confused. So you work in hex too much, and that's what happens to people. Right, so 4E48 is the hex value because this is in decimal. All right, so let me just .4E48, right? So if I just print this out, that's sort of the value that I should be looking at. So when I actually go ahead and jump into that offset, I get this value. What does this mean? It says 0002. It doesn't mean anything, right? But if you were to look at the spec sheet, which is this, and you jump into the structs format, the structure, you can see that the lexical structure inside the struct block, you have something like this. You will have, so every node starts with a node tag. You can call it a node. They call it token types, but it's just nothing but a tag, or it's an identifier that marks a node, right? So if I am going ahead and seeing this particular value, which is 0002, it means that's the end of the node that I have come up to. And then whatever follows after that is something else, right? Likewise, so I think there's a concrete value that was given over here. Let me see. Or I could actually do this. 0x 4e 48 minus 4. Oh, yeah, 44. Just checking. So right. How about I go back a few more bytes, just so that I can show you a full. Right. So now you see that this is a property because it's 0003, which is what the tag is for properties, right? So when you start a node, you start it with 0001. When immediately after that, after the node, after the tag, you have the node name, and then immediately after the node name, you have you'll have any padding bytes if you have to have some padding stuff, and then you'll have your properties follow it, which in this case will start with this value. Hopefully, if I can just go further back. I don't know in hex what that is, but I'll just go ahead and do 38. All right, I'm just trying to look for definitely missing something. Do, do, do. Oh, yep. Um, so this, sorry, I think I got this wrong. So according to the implementation that I've written, we see that struct item is what is something that I've already pulled out, which is my node. So if I wanted to actually go ahead and print this out, if is there this note, I'll just print node so that you can look at the entire thing. Right, so this, I've just made a small change over here so that you get to see exactly the node that was parsed at the I2C, whatever that address is. So right, as you can see over here, that's exactly the node that I was looking for, which is the I2C A30A200, and the end of its offset, the end of the node for it is at this particular offset, which is 20040. That's what we were looking at when we actually saw this. Where was that? That's what we were looking at when we saw this. The node ends at this particular value. All right. So, okay. Now, I hope that sort of makes sense. Any questions on this part? Is this tool useful? So I'm looking at the questions. Let me read it out. Is this tool useful in creating a board support package? So you mean the device tree? Yeah, so the device tree is not actually a tool, but the device tree is actually a, it's a file. It's sort of a description of what you can expect it's a file that's describing the system. It doesn't go to the detail as, here's this register and here's that register within the peripheral, but it does provide you information about, what is the memory map for a peripheral, what are the different pins that they may be using, etc. What are the interrupt numbers, all of that. So that is what a device tree provides. A device tree is primarily a file, which if you were to go ahead and compile using the device tree compiler, you will get a binary representation, which is the DeviceTreeBlob, right? In simple terms, you're just trying to say that, look, somebody who built a board, he would like to, he would like other developers to use the board. And in order for them to use the board, they need to know, things like what sort of peripherals are present, how are they configurable, how do you work with them, all of that. Now that information can either you can actually put it in the source code itself, that's one, or B, you can actually put it in a separate text file and say, here's the file. Go ahead and just, sort of parse this file or use this file if you want information about this kind of information. Right? I hope that makes sense. Yeah. Okay. I guess that makes sense. So let me actually go back to to our implementation. So actually walking through the implementation, right? And then right. So here's what happens when I actually take the same node. Now you saw that all I got when I actually parsed the node was this value, which is it's saying, okay, yeah, you're right. You've asked for that particular node. Yes, I've got it. I can show it to you. I can give you the name of the node. I'm just telling you I have the name of the node, but I've not gotten really what are the fields within it, right? I don't have that information. So what I've done is, you can now, because we've already written the parser, we can actually parse the DeviceTreeBlob to get all of the different properties that it contains. So let me show you an example. Let me sort of compile this and you will get an idea. Right. So here's what's happening. This particular node that we saw has all of these properties. And I've only printed out, the names of those properties. So if I was to show you that in a more visual manner, you can see this here. So let me put this here, and I guess you can see this, right? So if you were to see this, you'll see that, you'll see that this particular node has these properties, and I'm simply going ahead and capturing all those properties. And if there are any sub nodes within the I2C node, I'm capturing that as well, right? So compatible address cells, all of these are properties. And then you see this is another node that's nested inside the I2C node. And that's also something that I have access to. So if I wanted to look into it and I wanted to see what its registers are, what its offset is, I can also do that, right? Similarly, all the regulators, this is actually not very important unless you're working on something that's very, very electrical, engineering types. But yeah, anyway, so the entire thing is something that I can now print out, which is till LDO6, right? So that, now let's say right now I was showing you what? I was showing you the 3A2000, right? So was that it? So let's see. Yeah. So right now, let's just say I change this to, I don't know, 4, because that's what we have, right? So yeah, we've got 3 and we've got 4 and we've got 5. So let's just change that to, let's just change it to 4. See what we get, right? We should be able to get a different output because that peripheral, I have seen it. It is same. This is a different I2C peripheral. It does I2C, but that peripheral does not have a bunch of different regulators, etc. So if I was to run this, I should get this value. So let me go back and sort of verify that this is working. Sorry. Oh, I think the fastest way is to do that. Yep. So we are here. We were looking at 4. I think there's a, did I make a mistake somewhere? Treaty. I'm pretty sure they're all on the same bus though. Okay, I'll sort of jump into this and figure out you shouldn't be printing out the 3A2000. It should be printing out 3A24. Just try on a different one, see if that works. Seems to be printing out the same thing. Oh, sorry. I end up dated in 2 places. Makes sense. Right. Now, since this is a very tiny node, you only have these properties. So let's go back and check. Yeah, so we're looking at 3000. So let's just go back here. Yep. So if you see this, you have a bunch of different, compatible cells, address cells, and all of that. And then where's TCP? Oh, interesting. Some of them are missing here. Block frequency, pin control, GPIO at 2. Am I looking at the right one? Yes, you are looking at the right one. Oh, sorry. This was the one. I think I sort of probably gave the wrong addresses again. I'm looking in the wrong place. Yep. This is okay. It says 300, but let me just make that change again. That should help. Okay, so the output should remain the same. And if we were to go back and look at output, yep, this looks great. We've got the address cells, the size cells, compatibility, all of that stuff. And then we've got a GPIO pin that is specifically being, that's being specified for this particular peripheral. And it's, it's the offsets, the register values in there, and also the GPIO controller that you should be using and all of that. So we are now able to parse a particular node and say, okay, let's say I'm writing one of the drivers for a particular board. Let's just take this board only. If we are writing a driver, and let me show you what that looks like. So my drivers in boards, in HAL, source. I'll just go to Raspberry Pi 4 because the drivers are ready over there and they're already working. So if I'm writing a driver for something like, let's say, the UART, which is the serial terminal console. So this driver that I'm writing, I need access to those, base addresses and those address ranges. I need them. Now, the reason I need them is because if you look at my implementation, I need this register block to be written. The register block is basically the block that says, okay, that peripherals registers are mapped into memory at this location and these offsets, so that I can sort of start using them. If I wanted to read or write to them, I need them. And in order to write your drivers, you normally need that. What I generally do is, you look up the data sheets. Specifically in this case, I had to look up multiple data sheets because the Raspberry Pi 4 had multiple iterations and changes. And then one of them has their flash driver, their MMC controller at one location. The other one has it at another location. So that was a big big headache. If I, went ahead and did something like this, took the DeviceTreeBlob, just went ahead and parsed it and looked inside, I would have found this very trivially, right? So if you see over here, the base address for my GPIO peripheral is at this location, right? And then my so its start address is basically if you start address is this particular value where all of your memory mapped IO is sitting, which is this. And then if you add the offset to that, that's where you can, when you start reading and write to any location within FE000 plus hex 20,000, whatever, 200,000, you will be able to configure your GPIO peripheral. Same goes for your UART, same goes for your eMMC start. Or in other words, that is nothing but your embedded MMC controller. Okay, any questions on this part? Yeah, good question. I think somebody's asked a question that, Sharath has asked a question that DeviceTree and SVD files, are they the same? Some amount of overlap. I just discovered this just yesterday. There is some amount of overlap, but SVD files are what you call actual hardware description files. For example, I was just showing you this, right? I was showing you a driver. SVD files actually describe the registers themselves. These registers and their bits, what does each bit do when you set them or read them, or in which condition you should be reading them, all of that. All of that information is available in an SVD file. By the way, for folks who don't know, SVD files are system view description files. What they basically do is they describe the hardware. Usually these are provided for microcontrollers. I have not seen them a lot for regular the more powerful kind of hardware, that's Cortex-A chipsets, etc. People just don't put them out. I don't know, but RISC-V has SVD files as well again. So if you're having any RISC-V chipset, it has SVD files. So that's the primary difference. The SVD file is more of a hardware description file. It actually describes everything down to the bits in each register. The device tree is not going into that level of detail. It provides some amount of information like where is your peripheral mapped into memory, what is the memory address range, what is the offset, what are the pin control values, what are the interrupt numbers, all of that. Whether or not the device is actually supposed to be used, all of that information can be gleaned from the device tree, right? Okay. Hope that answers the question. Okay, the last part I have over here is, let me see if I can actually sort of complete this, because I was actually going to make this a very quick small tool that we can use to sort of get our work done. So yeah, I don't want to, like, this might take a while if I jump into this, so I'm not going to jump into it. Anyway, I'll sort of put this in, upload this to the repo. That's the Rustboot repo once the code is ready, so that you can take a look at this. Okay. Any other questions before we wrap for the day? Yeah, I think I have some interesting other videos probably coming up towards the later part of the next month. There's a couple of things that we're working on, which will be much more interesting. Not that this was, maybe helpful sometimes, because I found this helpful rather than having to do all of this work. Wish somebody would have sort of, given me this gyan, I don't know, a couple of months ago. Maybe I'd have saved myself quite a bit of time. Okay. All right. I guess there are no more questions. So that's pretty much what a device tree is. It's nothing but you simply go ahead and it's simply a binary file. I'm talking about the flattened device tree, not the device tree source. But in any, the device tree source is nothing but a file that allows you to describe hardware, specifically in the context of things like ARM, etc. Many architectures, not just ARM. You can describe your hardware, your board, your SoC, all of the different peripherals and all of the different elements that are present on that device, and those can be parsed at at runtime to figure out what's located where and how we can go ahead and use them. Now the thing is, you can do this at runtime, which is what Linux does. Linux actually parses the device tree at runtime. But then there are other operating systems, like real-time operating systems like Zephyr, etc., that because of constrained environments, you don't have the option of putting together this parsing logic, because parsing logic can be expensive. And also you don't have that space where you can load the DTP in and do all of this. So you might just simply go ahead and statically parse this and do exactly what I'm doing and generate header files which are nothing but constant values. So that's another thing that can be done. Okay. All right, that's it. I was hoping to actually wrap it up in like 35 or 45 minutes, but anyway, theory does take some time, I guess. So that's it from me today. Have a good day. Bye-bye.